Alright, so this is problem 7.17 out of Taylor. I had someone request me to do more problems out of chapter 7, so I'm going to do that. Before I start, if you wouldn't mind please liking and subscribing, I'd really appreciate that. And if you'd like to suggest a problem, you can do so on Twitter at PhysicsHelping. So problem 7.17 is an Atwood machine, and we have to use the Lagrangian method to find the acceleration. And, well, I guess I didn't include the figure, but it's just an Atwood machine. So hopefully that's completely fine with everybody. So we want to find the Lagrangian first, which is going to be our kinetic energy minus our potential energy. So of course, first we probably want to find our kinetic energy. So there's two masses here. There's mass 1 and mass 2. Each of those will have its own kinetic energy. 1/2 m1. And then the trick here, I'll call it x1 dot squared first, but I'll show you why that doesn't actually matter. So there's the kinetic energy of the blocks, but there's also rotational kinetic energy for the, I don't know what you would call I guess it's called the pulley, duh. So that has rotational kinetic energy, which will be 1/2 I omega squared. And they give us I. The moment of inertia for the pulley is 1/2 I omega squared, yeah. Okay, so first off, I wish I had the picture here, but I'll just draw it really quick. So you have some pulley system, and then you have, let's just say, mass 1, mass 2, maybe it's the other way around, but just to get the point across, they're both moving in the same direction, and the trick to see here is if we call this x1 and this x2, x1 plus x2 is equal to the length of the rope, which is a constant. That's not changing. So when you take the time derivative of both sides, you see x1 dot plus x2 dot is going to be equal to 0, or x1 dot equals minus x2 dot, or it doesn't really matter when you square it, because when you square it, the negative sign goes away. So I'm going to rewrite the kinetic energy a little bit as just 1/2 m1. I'm going to call it just x dot squared plus 1/2 m2, and that same x dot squared. So that's useful. Okay, so the next thing we want to do here is we want to rewrite omega squared. So omega is equal to, you might remember this from physics 1, the velocity over the radius, or in this case, just r dot over r, x dot over r. So omega squared is x dot squared over r squared. Okay, so I can add to this 1/2 I x dot squared over r squared. Okay, so that is our kinetic energy. Now we need to find the potential energy. Potential energy. So there's two things giving us potential energy. It's the two blocks, and it's gravitational potential energy. So that's the first thing I would show. And each one will just have their own kinetic energy. So we have minus m1 gx. Again, we're just saying that, call it x1, and then plus m2 gx 2. And again, if this is the case, x1 equals L minus x2, well, our potential energy is, we can kind of pick where we set our 0 to be. So a constant doesn't really change our potential energy. So because of that, we can simply replace these. I think I kind of skipped a step there, but if you wanted to, you could just say, speaking generally, m1 x1 g plus m2 x2g. But now we know the relationship between x1 and x2 in terms of our potential energy. So we can just rewrite this as minus m1 g x and then plus m2 gx. So there's a sign difference from moving it over. Hopefully that makes sense. This is kind of, I think, an equation that's important to know that some people tend to forget, and it makes the rest of this a lot easier. So potential energy, pretty easy. Now we're ready to find the Lagrangian, which is your kinetic energy minus your potential energy. Okay, so our Lagrangian then is 1/2 m1 x dot squared plus 1/2 m2 x dot squared plus 1/2 I, and in fact, let's see, I don't know if they actually give us the I. We'll just keep it as I for now. I x dot squared over r squared. Okay. And then minus the potential energy, of course. So we just say plus m1 plus m1gx minus m2gx. Okay. So we have our equation of, or we have our Lagrangian, so now we're ready to find our equation of motion. And the way that we do this is we say that the partial derivative of our Lagrangian with respect to x is equal to the time derivative of the partial derivative of our Lagrangian with respect to x dot. So let's start with the first part, derivative of what we just found with respect to x. Well, that's pretty easy. We just have these terms to worry about. So that'll be m1g minus m2g equals the time derivative of x dot. So let's see, pretty easy. Just take the derivative with respect to x dot, nothing crazy here. Oops, should be a single dot. I wasn't taking a time derivative yet. Okay. And now we take the time derivative, and I'm going to go ahead and factor out a g from the left-hand side. And now we get our x double dot terms. And I'm actually going to factor out x double dot. Okay. So with this in mind, we can now isolate for x double dot. And x double dot, which is just our acceleration, is this whole thing. m1 plus m2 plus I over r squared. Okay, and that's your acceleration. So I just want to re-emphasize a few things. We have our basic equation for the Lagrangian. We need to find our kinetic energy. And one thing that's helpful to know is this equation, that the lengths of the two wires, not the two wires, the length of the rope here between the two masses is equal to a constant. So that allows me to simplify the kinetic energy in the way that I did, and by using the fact that omega was equal to V over R, should be easy to see that this is then your kinetic energy. Potential energy kind of follows the same process. You need to use that same big equation here that I keep bringing up. And once you do that and you realize, well, there's just a sign difference and the constant is not important for our potential energy purposes, you should be able to get this. And then with that, you can find your Lagrangian. After you do write down your Lagrangian, you write down the Euler Lagrangian to get the equations of motion, and then you just simplify for x dot. So hopefully that makes sense. If it did, please like and subscribe, and I'll do some more problems out of Chapter 7.